This is the third part of the AP Calculus final review series, and this is for BC only because we're covering chapters 6 and 7, which AB did not cover. So we're starting off with chapter 6, which is about more derivatives. We have exponential and logarithmic functions, implicit differentiation, inverse trig functions, and a lot more applications as well. So let's get started. First of all, exponential functions. Most of you probably know what E is. E is the exponential constant, like 2.718 approximately, but it's also equal to the limit as n approaches infinity of 1 plus 1 over n to the power of n. And there are a few other variations of this formula, but I'm just going to include this one, and you can kind of derive the other ones using this one. But the reason why this is important is it's basically compound interest. This is the compound interest formula because it has to do with 1 plus 1 over n, which is a 1% or 100% rate over n times compounded in a year and then n times compounded in a year. So that's basically what E is equal to. E to the power of x is called the natural exponential function because it's very special. And the reason why we'll get to in a bit is because of its derivative. So the derivative of e to the power of x is actually just going to be e to the power of x. That's why it's special, because its derivative is itself. So d dx of e to the power of x is e to the power of x. Now, what if we have something like 2 to the power of x? The general formula for any function that's a to the power of x, where a is a constant, is going to be a to the power of x. But unlike e to the power of x, it also has this coefficient ln a. Now, ln a is going to just be a constant no matter what, because we said a is a constant, so the natural logarithm of a will also be a constant. The reason why for e to the power of x is just e to the power of x is because technically it's still multiplied by ln a, but since a is e in this case, it's going to be ln e. And ln e is just going to be 1. So it's just by itself. Ln, though, is the natural logarithmic function, and it's the inverse of the exponential function. It's basically log base e of x. Now, what about the integral of an exponential function? We have the integral of e to the power of x dx is, believe it or not, e to the power of x. And then plus c, obviously, because it's an indefinite integral. What about the integral of any a to the power of x dx? You can sort of derive this by like undoing this rule right here, and you'll get it's going to be a to the power of x over ln of a, which kind of makes sense because if you take the derivative of a to the power of x over ln a, derivative of a to the power of x is going to be a to the power of x times ln a, so the ln a's will cancel out, and you're just left with a to the power of x, which is what we want, and then obviously plus c. So that's basically exponential functions. And then there's logarithmic functions as well. And the book goes in a different order, talking about implicit differentiation and inverse trig derivatives before logarithms. But I feel like if we're talking about exponentials now, we should also talk about logarithms now. I think the reason why they're not talking about logarithms before this is because to prove it, you're going to need to use implicit differentiation. But I'm not going to prove it here because we don't have time for that. I'm just going to review the formulas. So for logarithm, the derivative of ln x is going to be equal to 1 over x, which is kind of surprising. But and then, as you might imagine, the derivative of log base b of x so where b is any constant, is going to be 1 over x times ln b. And the ln b will be in the denominator. And then we can take integrals too. The integral of 1 over x dx is going to be ln x. ln absolute value of x though. So that's the key difference here. The reason why is because x can be positive or negative here, but if you just write x here, ln of a negative number doesn't exist like in the real number system, which means that we cannot take the ln of a negative, therefore we have to put the absolute value on. Now, that's just taking the derivative, the antiderivative of 1 over x. What about the antiderivative of ln x? Well, it's a bit more complicated, and there is a proof for this, but we still have not learned how to do it. It uses something called integration by parts, which is actually a part of chapter 7. The integral of ln x is going to be x times ln x minus x plus c. So it probably won't come up that often, but something you might want to memorize in case it does. So that's exponents and logarithms. Moving on to inverse trig derivatives. So again, I'm skipping implicit differentiation for now because we would need to use that to prove inverse trig derivatives, but since we're not proving it, we can get back to it. I just want to go through all the rules and stuff you have to memorize first, and then go through the applications and the things that actually use like examples to teach. So we got inverse trig derivatives. The derivative of inverse sine x is pretty surprising, actually. It's not going to be equal to something in terms of another inverse trig derivative or inverse trig or trig function. It's going to be the 1 over the square root of 1 minus x squared. And you can prove it using right triangles, trigonometry, and like I said, implicit differentiation. We'll get to that in a bit, though. I might just show you how to prove sine in case you find all these too much to memorize, and then you can just derive it on the test. I personally encourage memorizing it here because the test might be a time crunch. So you might not be able to derive it, but if you do want to just derive it, then I'll show you how to derive just sine, and then you can apply the same principle for the others. For inverse tangent, it's 1 over 1 plus x squared. These two are probably the most important ones you should memorize. You'll notice I didn't do cosine yet, and I will get to that. It's just, I'm going to do inverse sine, inverse tangent, and inverse secant first, and then I'll show you a little pattern with the others. So it's really memorizing just 3 of them and then like knowing a pattern. So you don't really have to memorize all 6, and I'll explain the pattern soon. But inverse secant, it's going to be 1 over absolute value of x times square root of x squared minus 1. Okay, now that you got all 3 of these, the cofunctions of each of these. So the cofunction of sine is cosine, cofunction of tangent is cotangent, cofunction of secant is cosecant. The cofunction of each of these is just going to be negative. So inverse cosine, the derivative will be negative 1 over square root of 1 minus x squared. Inverse tangent is going to be negative 1 over 1 plus x squared. And inverse secant is going to be negative 1 over absolute value of x times square root of x squared minus 1. So that's why I'm not writing it on the board, because it'll take too long. Is just put a negative in front of the original function. I think I'm actually going to talk about the derivatives of inverse functions before implicit differentiation, because implicit differentiation takes some time to understand, but derivatives of inverse functions is just like a rule you can memorize. So let's say we have g of x, which is the inverse of f of x. So in the first video, in chapter 1, we reviewed inverse functions, and this is why. Because we need a formula to take the derivative of the inverse function. And you might think we don't need it. If it's x squared, we know the inverse would be root x, and then we can just take the derivative there. What if you're given a table instead of a function? And you know that the function has a point like 0, 2, 1, 5, and then 2, 7, 3, 8. And you want to find the derivative of the inverse. Let's say the inverse is g. You want to find the derivative of g at 7. And obviously, you're given another line for the derivative of f. So this is x, this is f, this is f prime. And these are some arbitrary values like -1, 0, 5, -3. How would you do this? Well, that's where this formula comes in, which is why we're learning it. Oops. Okay, so the formula for this is going to be g prime of x is going to be equal to 1 over f prime of g of x. So that looks a bit complicated, but there's some parts we can take out. So we know that if there's a point a comma b on f of x, it's going to be b comma a on its inverse because it's just reflected over the line y equals x. And any point here just becomes here. So it's going to be AB to BA. How does that help us? Well, we know if we're saying g prime of x, that means the input is b. So g of x here, that's going to take in b and output a. So basically what this is saying is instead of going through all of this, it's going to be f prime of a, where this is a. So obviously I cannot write that here because we're defining things in terms of x in this formula, but just know that it's not as complicated as it looks. You just inverse the pair and then take the x value of that pair. So since the x value of the inverse is going to be b and the y value is going to be a, you just take the x value of the original function, which is the y value of the inverse, a. I'll give you an example. So let's say we have we have f of 2 is going to be 8 and f prime of 2 is going to be 4. So what this is saying is, let's say g of x is the inverse of f of x, find g prime of 8. Now the reason why it's not saying g prime of 2 is because, like I said, you switch the order of the ordered pair. So now 8 is going to be the input and 2 is going to be the output. So basically this ordered pair, meaning g of 8 would be 2. That's something to keep in mind because when we apply the formula, we get 1 over f prime of g of 8. And we said that's going to be 2. And luckily we know f prime of 2 is 4. So we can just replace f prime of 2 with 4 and your answer is going to be 1, 4. It's not that it's kind of complicated, especially because it's not very intuitive, but these are mostly going to be on a table problem. It gives you a table of values and you have to do something with it. Similar to previous problems that are like, it gives you f of x and g of x, and you know h of x is the product of f and g of x, and you want to find h prime of x, then you have to apply the product rule using the table. But that's neither here nor there. Okay, finally we get to implicit differentiation. After this is only the mean value theorem and improper integral. So we're almost done with chapter 6. Implicit differentiation, though, is a pretty big topic. Most common applications are for circles. And I'll actually show you an example first to get you started. Implicit differentiation is basically when it's not a function and both x and y are together in the equation rather than y is isolated. The reason why we have like y is equal to 2x and we can take the derivative of that is basically saying dy dx is equal to 2 times dx dx. You're basically taking each variable and you're doing d that variable over dx, and you're doing that for both variables. And you'll simultaneously take the derivative of this. Dy dx just simplifies to d dx or y prime or f prime or something like that. Dx dx is just 1 because it's dx over dx, which is just 1. So that's why we never write that in an actual explicit differentiation problem or the regular differentiation we've been doing all this time. Implicit differentiation, let's take an example of x minus 1 squared plus y plus 4 squared is equal to 16. How are we going to find the slope function for this? Well, you just take the derivative of each part of the function. So derivative of x minus 1 squared gives you 2 times x minus 1, and then chain rule, but this coefficient of x is just 1, so we don't really need to apply the chain. This is times dx dx, but that's just times 1, so I won't write that here. And then we have, you bring down the 2, you have y plus 4. Again, chain rule, the coefficient of y is just 1, so we don't have to do anything about it. And this time we do have dy dx, since the variable being differentiated is y and not x. So we don't write dx dx, we write dy dx, which does not cancel out. And derivative of a constant is just 0, so we have equals 0. Now, what you can do is move the 2x minus 1 to that side. So you're left with 2 times y plus 4 times dy dx is equal to negative 2, because we moved it to the other side, times x minus 1. And the reason we're doing this is we want to isolate dy dx. That's what we want to isolate. So we divide everything, or first we can divide by 2 because there's a 2 in both sides, and then we divide by y plus 4, and we get dy dx is equal to, well, negative times x minus 1 just becomes 1 minus x, and that over y plus 4. And that's going to be your derivative for this circle. That's implicit differentiation. There is a step-by-step process that I can go over, but I feel like an example is best. First of all, you differentiate both sides with respect to x. We just did that here. Second of all, we use dy dx notation. That's more of a reminder than a step. We apply chain rule when we are differentiating y. That we did over here, because when we differentiated this part of the function or part of the equation, we used a dy dx. And fourth of all, we solve for dy dx, which is all this algebra we just did in the end. All right. Finally, one more application of implicit differentiation is the proof to derive inverse trig functions, inverse trig derivatives. So let's take inverse sine. Right triangle trig is pretty key to this derivation. So let's say inverse sine of x, right? This is a function. Let's say it's equal to y. So we can rewrite it as x is equal to sine y by taking the sine of both sides, which cancels out the inverse sine on the left-hand side. Sorry, sine of y, not sine of x. Which means that y is the angle, because you're taking sine of y, so y has to be an angle, and x is going to be the ratio of the opposite to the hypotenuse. Which means if we keep the hypotenuse as 1 to simplify things, the opposite is going to be x. And we can make this 2 and 2x, but why should we do that when we can keep it as x and 1? Remember, trig functions are just ratios, so it doesn't matter what you can put. Since it's all similar triangles, you scale it up, you scale it down, it doesn't really matter. Now, using Pythagorean theorem, we can find out what this other side is. That's going to be 1, the hypotenuse is equal to x squared, plus this other side, which I'll just label s squared. So you solve for s, you get 1 minus x squared is equal to s squared. So you just square root both sides and you get 1 minus x squared. So this is going to be square root of 1 minus x squared. Why does that matter? Well, finally, let's take the derivative of this. It's going to be implicit differentiation since it's sine of y. It's not just y isolated by itself. So first, derivative of x is just 1. Because, there's a dx, but simplifies down. Derivative of sine y is going to be actually cosine y, but then multiplied by dy dx because we just took the derivative of something relating to x. Solving for dy dx, we get dy dx is equal to 1 over cosine y, which is going to be equal to secant y. That is a valid answer, except for the fact that it has something to do with y, and we want it in terms of x. Now, of course, we can just plug in this equation into y. So we say the derivative would be secant of inverse sine of x, but that just looks very complicated. Instead, we can use this right triangle, which is why we drew the triangle in the first place. Dy dx is equal to secant y. If this is y, what's the secant? Well, cosine is going to be adjacent over hypotenuse. So secant is going to be hypotenuse over adjacent, which means that it's going to be 1, which is the hypotenuse, over root 1 minus x squared, which is the adjacent. So it's going to be 1 over square root of 1 minus x squared, which is exactly what we said back when we introduced the formulas, right here. 1 over square root 1 minus x squared. So I'm just showing you that proof. You can choose to derive the rest of them as well on the test if you want. But moving on, our next topic is going to be the mean value theorem and the mean value of a function. So the mean value of any function f of x is just going to be the average value of f of x. I'm denoting it with a bar here because that generally means average. It's going to be 1 minus b over a, because we do need an interval to find the average value. You just cannot say the average value over like the entire domain, because that's going to be infinite. But the average value over an interval a comma b is going to be 1 over b minus a times the integral from a to b of f of x dx. And you can kind of visualize it on a graph. If we have this graph here that looks like this, and you want to find the average value of it, you take the area. That's probably a bad graph. You take the area under the curve, and then you divide it by 1 over b minus a, which gives you somewhere around here. And that's going to be your average value. Now, notice one key thing about this. This average value intersects with the original function in a few places, meaning the original function has a few places where the value of the function is the average value of the entire function over that interval. That is something called the mean value theorem for integrals. In general, it's not called the mean value theorem. Like in other textbooks, it's not called a mean value theorem. The mean value theorem is something else that we'll get to. But in this book, it's called the mean value theorem for integrals. And there's also something called the mean value theorem for derivatives, which is generally called the mean value theorem in other textbooks. But for integrals, it's going to be if f is continuous on the closed interval ab, that means there is at least one point c in the open interval ab such that f of c is equal to this 1 over b minus a, this average value of the function. And don't be confused by average and mean, why I'm using them both. Average and mean are basically the same thing, especially in math. Mean, average, both generally mean the same thing. Of course, there's stuff like arithmetic mean, geometric mean, and things like that. But in this case, mean is just the sum of all the items in a list divided by the number of items. So since it's a function, it's going to be infinite, which is why we need integrals to calculate it. So it says there exists at least one f of c. And this is only if it's continuous on the closed interval, just like other theorems we've looked at this year. Then there's the mean value theorem for derivatives, which says if f is continuous on the closed interval ab and differentiable on the open interval ab. That's a key point. That means there exists at least one c such that f prime of c, the derivative at c, is equal to the average rate of change of the interval. So f of b minus f of a over b minus a. So what it's saying is, if you have a function like that over this interval, the average rate of change is basically the secant line that goes through the endpoints. That means there exists at least one other tangent line that is parallel to the secant line. So these both actually are parallel to the secant line somewhat, which means that the mean value theorem does apply here. And it does because it's continuous on the closed interval and differentiable on the open interval, which are the two conditions for this theorem. These questions come up a lot, especially on something like an FRQ. It says use the mean value theorem to find the value c such that it's parallel to the secant line or something like that. Good to know. There's also something called the Rolle's theorem, and that is not very useful because it's basically the mean value theorem for derivatives, but a very specific case for that. It says that if f is continuous on closed interval ab and differentiable on open interval ab, the general stuff, then and f of a equals f of b. That means there's at least one critical point or point where f prime of c equals 0 in the interval. Why is this? We can use the mean value theorem to prove this. Well, the mean value theorem says it's equal to f of b minus f of a over b minus a. Well, if f of b equals f of a, then this numerator will just be 0 since they're equal to each other, and b minus a will not be 0 since they're not the same point. So that means f prime of c equals 0, which is literally what Rolle's theorem says. So Rolle's theorem, you can easily just derive in a second from the mean value theorem for derivatives. So it's not that important that you know it. You can obviously derive it from the mean value theorem for derivatives, but maybe you want to know what it's called. So in an FRQ, you can say using Rolle's theorem. Final topic for chapter 6 is improper integrals. Improper integrals are basically integrals that can be infinite. So either there are two types. Type 1 is one of the bounds is infinity. So it's going to be like 0 to infinity of or 1 to infinity is a better example of 1 over x dx. The second type is when the integrand becomes infinitely large, and I'll get to that in a second. But in this case, what we're going to be doing is we're actually going to use a limit because you cannot really put an infinity in the bound. You need to do limit as a or b, whatever, it doesn't matter. A approaches infinity of integral from 1 to a of 1 over x dx. Now ignore the limit for a second and just take this. Well, what's the integral of 1 over x dx? It's going to be ln absolute value of x. And then this is an antiderivative. It's not the general one. Sorry, it's going to be a definite integral. So it's going to be from a to 1 or 1 to a. And you just plug that in and you get ln times absolute value of a minus ln of absolute value of 1 is just going to be 0. So it's just going to be ln absolute value of a. And now you take the limit as a approaches infinity of this. And actually, this is when you plug in infinity into ln, you're actually going to get infinity. So we say this diverges. Which is interesting. Basically meaning it's going to infinity, but we cannot really write that, so it diverges is what we call it. The second type, I'll just briefly go over it, is when it's something like integral from 0 to 3 of 1 over x squared dx. Now, the bounds don't become infinity because, as you can see, there's no infinity in the bounds. However, when you plug in 0 in here, it certainly does become infinity because 1 over 0, well, we take it to be infinity. So you do the same thing here where you write limit as a approaches 0 of integral from a to 3 of 1 over x squared dx. So now what is the antiderivative of 1 over x squared? Is going to be equal to negative 1 over x. You take the, you put 3 in a here since it's a definite integral. So you get negative 1/3 plus, because the negative and negative cancel out, 1 over a. And you want to take the limit of this as a approaches 0. We're actually going to end up with infinity down here, meaning this also diverges. So these are actually really bad examples because most of these do not diverge. There are some that diverge, like these two, but some of them do not diverge and actually come up to be a pretty nice number. All right, that's it for chapter 6. We covered a bunch of tools and applications of derivatives, just like chapter 5, but this is just going more in depth. Okay, chapter 7. Now, I'm not going to go over everything in chapter 7 because there are stuff that someone did learn, but they're not going to be on the final. And since it's a final review, I'm not going to go over unnecessary stuff. So we're starting off with related rates, which is pretty important. I'm going to give you an example problem for related rates since it's probably confusing without an example problem. Let's say we have a triangle, or since it's a real world application, let's say there's an intersection and Bob here is moving away from the intersection, or Bob is 40 feet away from the intersection, while Alice is 30 feet away from the intersection in this direction. Bob is riding on a bike at 5 feet per second away from the intersection, while Alice is riding or is walking towards the intersection at a rate of 2 feet per second. There's a distance d between them. How fast is that changing? Is it increasing, decreasing? That's what we want to know. How can we do this? Well, it's a right triangle, meaning Pythagorean's theorem. We write x squared plus y squared equals, I like to call it d for distance, d squared. Let's plug in what we know. We know 30 and 40 at this moment in time. So 30 and 40 make 50 if you use Pythagorean's theorem. So the distance right now is 50. How can we use that? Well, we want to know how fast the distance is changing. So let's take the derivative of this. Since whenever we're concerned with the rate, we take the derivative. Derivative of 2x is, derivative of x squared is 2x. Now we're going to add something called dx dt. So it's kind of like implicit differentiation, but it's with respect to t. So even for the variable x, you still need to add the dx dt. The reason why is because all of this is with respect to time, since it's feet per second. Well, this is just feet, meaning we are taking the derivative with respect to time. So we do the same thing for y. We get 2y times dy dt. And we do the same thing with d, and we get 2d times dd dt. Now, we want dd dt. And look, believe it or not, we have 1, 2, 3, 4, 5 other variables in this equation, 6 including the one we want to know, and we literally know every other variable. It doesn't look like it, but what's x? Well, that's just, we'll arbitrarily call this x. This is 30 feet. We know that's the distance. X is 30 feet. Y is 40 feet. We know that. Dx dt is the rate of change, which is -2 since it's moving towards. And dy dt is this rate of change, which is 5. We know everything. And d we know is 50 because we found that. We just don't know dd dt. So plugging it in, 2x. So x is 30, so 2x is 60. 60 times -2 because it's moving towards the intersection, plus 2y. Y is 40, so 2y is 80, times dy dt is going to be +5, so it'll be 5, is equal to 2d. D is 50, so 2d is going to be 100, times dd dt. Now, simplifying, we have 60 times -2 gives us -120, plus 80 times 5 is going to be 400. So 400 minus 120 is going to give us 280, is equal to 100 dd dt, which means that dd dt is going to be equal to 280 divided by 100, which is 2.8. And since that's a positive number, it means the distance between them is increasing. So that's just a sample related rates problem. There's also other ones about volume and surface area of 3D figures and so on, but I'm just going to show you this one example for related rates because you can use the same process for all of them. Basically, the process is draw a diagram to show what variable is what. Use implicit differentiation with respect to time for every single for the entire equation generally, and then you just want to solve for one rate or one, maybe even one variable. You know all the rates. You just want to solve for d, for example. Unlikely, but it's possible. You just do that, and then you get your answer. All right. There's two actually more types of related rates. This is Pythagorean theorem related rates. There's volume related rates, and then there's trig related rates. But all three of them are kind of similar in terms of the process. I'm just going to go through this one for now. All right. Another thing we learned in chapter 7 was U substitution. U substitution is basically anti-chain rule. That, and then we also learned differential equations, which is going to be the next big thing. I'll just quickly go through U substitution. U substitution is going to be if you have something like, let's say, derivative of ln x over x dx, integral of ln x over x dx. How would you solve that? Well, what you can do is, well, let's say some function u is ln x. What's the derivative of u? Du is going to be 1 over x dx. How does that help us? Let's rewrite this a bit. We have integral from ln x times 1 over x dx, since we're just moving the ln x off the numerator. well, that's weird. We have ln x, and we have 1 over x dx, which means we can rewrite this as integral of u, because u is ln x, times du, because du is 1 over x dx. And this is a very simple integral problem. Integral of u du, if u is just some random variable, where you can take the antiderivative, it's going to be 1/2 u squared plus c. Now, finally, we plug back the ln x here, and we get 1/2 times ln x squared plus c. That's going to be this derivative, this integral. There's one more thing to talk about with u substitution. If you have a definite integral, like from 2 to 6 of the same problem, what you're going to do is you convert it to u. That's probably a bad example. Let's go from 1 to e of ln x over x dx. You can rewrite this as integral of u du, but since it's u, you have to convert the bounds to u. So you just plug in these bounds into this equation for u, because these are x equals 1 and x equals e, but we want u equals something and u equals something. So plugging in 1, you get ln of 1, which gives you 0, and then we have ln of e, which gives you 1. So you have just from 1 to 0. So then you don't even have to convert it back to ln x. You can just keep it as 1/2 u squared plus c, and then just do from 1 to u. So you can ignore the c in that case. And then you from 1 to 0, you do 1/2 times 1 squared, which is 1/2, minus 0 gives you 1/2. So in this case, you don't even have to go through the trouble of converting it back to x. You can just keep it as u if it's a definite integral. And you change the bounds. You have to change the bounds. That's it for u substitution. Finally, we have differential equations, and that's a big thing. So differential equations, there's a condition that has to be met. It has to be quote unquote separable. What that basically means is you need to get all the y's and dy's on one side and all the x's and dx's on one side. Let me show you an example of one that is separable and two that aren't. Let's say dy dx is equal to x over y. Pretty simple, one of the more common differential equations. This is how a differential equation looks, by the way. It has dy dx equals something in terms of x and y, and to solve it, you need to separate the variables. Basically, move all the y's to this side and all the x's to the other side. So you just multiply both sides by y, and you get y times dy. And then you multiply both sides by dx, and you get x times dx. So y dy equals x dx. Take the integral of both sides then, because you want to integrate it. Since we already have a dy and dx, you take an integral to undo that. And integral of y dy is just going to be 1/2 y squared plus c. And I'm going to write plus c 1. And this is equal to 1/2 x squared, because it's just integral of x dx, plus c2. And you can actually get rid of c1 and c2 and just rewrite it as c, because you're combining two constants to form another constant. So you have 1/2 y squared equals 1/2 x squared plus c. And obviously you can simplify this to get y equals something, but you also need to solve for c. So that's an important thing. If you're given an initial condition like 2, 3 is a point on the graph, then you can plug in 2, 3 and solve for c. If you're not, then you just have something called a general antiderivative, which has a plus c. Think of it like the general antiderivative. This is the general solution to the differential equation. Now, what about inseparable differential equations? dy dx is equal to x minus y. It looks fine. You just add y to both sides and then multiply by dx. Yeah, but if you add y to both sides, you'll get y plus dy dx is equal to x. And then when you multiply by dx, you also have to multiply this term by dx. Since it's now multiplied to dy dx, it's added to dy dx. So it'll become y times dx plus dy equals x dx, which just looks horrible. That is not valid separation of variables. So this is inseparable. and therefore we cannot solve this differential equation. There is another common type of inseparable differential equations, but this is the most common type because it's x minus y and it's not like over y. You could also say dy dx is equal to x plus y, which is another common type. Again, it's the same thing where you subtract y from both sides, which looks fine, but it really isn't because you get the same exact thing. Okay, now that we know how to solve differential equations and how to identify whether they're separable or not separable, I'm going to go over slope fields. There is something called Newton's law of cooling, but it's not that major. We briefly talked about it, but it just basically says, oh, it's an exponential function that approaches room temperature. Let's say you have coffee out. It's going to be an exponential function that kind of approaches room temperature, and then you have some constants you can solve for given times, and then it's mostly word problems related to that. But slope fields are basically, you have a differential equation, dy dx is equal to x over y. And slope fields help us when it's not separable. So in this case, it is separable, but that's because we want to compare it to the actual answer. I'm actually going to change it to dy dx is equal to x. First, let's draw the slope field, and then we'll solve it to see if our slope field and equation compare. If it's just equal to x, what we do is basically for any point on the slope field, so 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, and then 1, 0, 1, 2, 0, 3, 0, and then 1, 1, basically every single point, you plug in that point into the differential equation. If we had both x and y, we would plug in both x and y coordinates at the point, but we only have x, so we would plug in the x coordinate. When x is 0, basically this entire y-axis, the slope is just going to be 0 since you plug that in. I'm going to use a different color for this to show you the slope. So you have x equals 0, so the slope equals 0. Voila. What about when x equals 1? Slope will be 1. So you draw somewhat like a slope of 1. 2 will be a bit steeper, and I'm kind of exaggerating its steepness right now. And since it's on a computer, it's pretty hard to draw a proper graph. But you can also do the negative side. -1 gives you a slope of -1. -2 gives you a slope of -2. Okay. Now, what does this look like? Well, if we were to draw a curve that fits this, we would get something like it goes down this way and then back up. And it looks kind of like a quadratic. Does that fit our equation? Well, let's separate variables. This time we don't have to divide by anything or multiply by anything. From this side, we just have to multiply by dx to get that here. So we get dy is equal to x times dx. Integral of both sides. Integral of just dy is going to give you y. And integral of x dx is going to be 1/2 x squared plus c. Now, we're not given a specific point, so it can literally be any of these curves on the graph. Sometimes they ask you to draw a few solutions that are possible on the slope field. Sometimes it just asks you to draw one. So it does fit because this is a quadratic, and this kind of looks like a quadratic. So that's basically what a slope field is. Especially when it's not separable, it's used to kind of find the graph of the function. One thing to note about slope fields, are there any parallel tangent lines here? Well, all of these are 1, meaning all of these are parallel to each other. Why is that the case? Well, that's because this only depends on x. So y doesn't matter. So no matter the y on this vertical line, it's going to be the same tangent line because it only depends on x. So you can use that to identify the differential equation given the slope field. Like if you were given this, you can say, oh, they're vertical parallel tangent lines, meaning that it doesn't depend on y, it only depends on x, and then you can somehow find out that it's dy dx equals x rather than dy dx equals y or x over y or something like that. All right, that's all we learned for chapter 7. Oh, there's also Euler's method, which I will cover. Yes, Euler's method is basically going to be where you're trying to approximate a point. Earlier, we were using tangent lines to approximate a point, but this one, you're using multiple tangent lines to approximate a point. So you have delta x equals like 0.5. And I'm going to do a pretty short example. Let's say you're starting at x equals 0, and you want to approximate x equals 1. You're given the differential equation dy dx is equal to x plus 3 over 1 minus y, for example. And obviously this is separable, but it's just an example. Let's say at x equals 0, the point is 0, comma 1. What you're going to be doing is, we know the point there, and we can plug in that point into here to find the slope, because it's a differential equation. It gives you the derivative or the slope. What can we do with a point and a slope? We can write a tangent line, point slope form. Let's do that. We have y equals, and then we have to plug this in to find the slope. So actually, I just realized 0, comma 1 is impossible, since when you plug in 1 here, you're going to get a 0 in the denominator. So let's do 0, comma 0. When you plug in 0, comma 0, you're going to get 0 plus 3, which is 3, over 1 minus 0, which is 1. So 3 over 1 gives you 3 as the slope. And then x minus 0 plus 0 just simplifies down to 3x. Very nice tangent line. Simple. What do we do from there? Well, previously, we would use this tangent line to approximate x equals 1 by plugging in 1 and get, y equals 3. But that's a very bad estimate. Let's say it looks something like this. Well, you use this tangent line to approximate this. That's a very bad estimate. But let's say you use this tangent line to approximate this point. It's still a pretty bad estimate. But now we know that the slope of that would be somewhere around here, which does bring it down. And then you use it to approximate this next point, and it brings it down even further. And it's much closer than just approximating it by the first tangent. So we approximate the next point. What is the next point? Well, that's why we said delta x equals 0.5. We're jumping by 0.5. So we plug in 0.5 into the equation, and we get 3 times 0.5 gives you 1.5. So it's going to be 0.5, comma 1.5. Now we plug that back into this to find the slope, and therefore find the tangent line. You plug in 0.5, you get 3.5 in the numerator, and then negative 0.5 in the denominator, because it's 1 minus 1.5. So if you were to simplify that, you would get negative 7. Y equals negative 7. And it does look like what we said is going to be like a big jump like this, because it's 3 over here and negative 7 over here. So it's a good thing we didn't jump directly to x equals 1, and we were using Euler's method instead. So it's not y equals negative 7, and then x minus 0.5, because point slope form, and then plus 1.5. Now you plug in x equals 1, because now we're jumping from 0.5 to 1. We're jumping by another 0.5. So like I said, this is a short example. Usually you want to have more steps in between. So it'll be like delta x equals 0.2 or something like that. And you have multiple steps to make it more exact. But in this case, we plug in 1. We get y equals negative 7 times 1 minus 0.5 is going to be 0.5. So negative 7 times 0.5 gives you negative 3.5. And then negative 3.5 plus 1.5 gives you negative 2. So it's going to be 1 comma negative 2. And that's it, because we got our point that we wanted. X equals 1, well, 1 comma negative 2. That's a good approximation, or better approximation of the point of it. Now that's it for chapter 7. Obviously, there's a few more things I didn't cover, most notably integration by parts and partial fraction decomposition. We didn't even learn partial fraction decomposition yet. We did learn integration by parts, but it's not going to be on the final, which is why I'm not reviewing it. And I didn't really go over Newton's law of cooling that in detail. So if you want, you can just review that. But this video is already like 50 minutes long, which is why that's it for this video. It's going to be the final part for the semester 1 final review series. We covered chapter 6 and chapter 7. And yeah, good luck for your finals.